Hello, everyone. I think we are already already live. So let's go. I'm here today to talk about front-end concurrency control with specific with file uploads. Who am I? My name is Miguel. I am a full stack developer at CodeMiner42. If you want to check my everything related to me, you can check my beacons, triathlete.dev. Um, I do amateur triathlon. I have four cats, three dogs. I like to play tabletop games when I have time. Not too much recently, but yeah, that's life. CodeMiner42, it's always hiring good engineers. So if you want to check it out, just take a read on our website. Also, this topic, I wrote blog posts to CodeMiner42 blog. So if you think you have some doubts yet, you can check the blog post, and everything related to the code, it's on our repository. You can check the link below. Each of the each of the use cases we will talk today are on separated PRs, so you can check each code, and it's easier to see what is changed. Yeah, that's it. If each use case has its own PR, so if you have doubts, you can comment or open issues on the public repository. I will be glad to answer you there, or on YouTube. What else? So let's start. Let's talk about the good things. A thread. Um, it's a computer science in the execution of running multiple tasks or programs at the same time. Each unit capable of executing code is called a thread. Of course, inside computer science, thread can mean different things in different moments. But for us right now, it's important to know what is related to the browser itself, because our code will run on the client side. So the main thread by default, and JavaScript as default, is a single threaded. So all the JavaScript on our page are running on the main thread. Of course, we can have a lot of things changing that. But yeah, let's go through everything. Also, we will work with file upload, but I don't want to connect with Amazon and everything related to that. So we are using local stack that, as you can see, you can like emulate a lot of cloud services as the S3 bucket and a lot of other things. So if you need to have like end-to-end testing locally, and you don't want to like hit AWS APIs and everything else, or you want to create a proof of concept and don't want to connect with AWS, you can use local staff or other libraries that can help with that. And you will have like a local server mocking those things, and it is the same thing. When you change it local stack to AWS, it will work like a charm, because you are using the same SDKs and same APIs. You are just like pretending that you have like a cloud service. Also, I want to say that everything related to the React thing as a whole, it was not a focus here. You can see we have like a root page, handling a lot of UI logic there, because it was not my main point. So if you want to improve that, you can open a PR there. But our main focus is to talk about the concurrency on JavaScript and with files upload. So just to have that in mind. So this is the code we have on our repository. You can see we have a class named like local S3 simulator with a bunch of stuff just emulating our S3 with the local stack. Every time we have like ellipses, it's because I am not showing the code, but you can see it's very straightforward. It's just our S3 simulator with some default setup that we need when we are instantiating our simulator, and some methods we will need to like check if the bucket already exists, to create the bucket, and to generate it and sign it upload URLs that I will talk right now. So to be able to upload, I want to use pre-signed URLs, because doing that, you don't need to like create folder credentials for all our buckets on S3. So you can just create pre-signed URLs. So your user will be like able to only check the files you are getting back to them. So it's super secure, and you have more. You don't need to do a lot of setups on the AWS side. But one of the things is that they are to check the data integrity for those pre-signed URLs. We need to use the MD5 hash algorithm, and you will see that if we could use, I don't know, other ones, it will be easier. But that's what it is. So let's start. We have like our duck rules here. We will have 3 different ducks handling what is needed. One will generate the MD5 hashes. The other one will generate the pre-signed URLs. And the other one will perform the uploads with using the pre-signed URLs and everything else. Also, yeah, we have a S3 upload service that is using our local S3 simulator, and that's it. We have some hidden logic because it's very straightforward, and you'll see the generate signed upload URLs and upload single files on other examples. But just to illustrate that we have this another class on our infra folder. So for our first use case, we will handle our upload as a sequential logic. So each duck has to wait for the other duck to finish their work so they can go through, and each duck type need to wait the other duck type to finish their work so they can go through the process. So every time an MD5 file is generated, then we will call the next one, and then from the file pre-generated URLs, and then the file upload, and that's it. That's super sequential and the lowest possible way I think we can do it, right? So let's take a look on our use case about the sequential upload. We are using our upload service, right? So super straightforward. We have our upload file sequentially that will receive the files we want to upload. Then we have just a for loop looping each file and generating each MD5 hash and pushing that so we can use it later. And then the same thing for the signed URLs. Then the same thing for uploading the files itself. You can see we use the files and the pre-signed URLs to be able to commit or upload, and that's it. That's our code. Of course, because we have like the code inside the generate signer upload URLs and the MD5 hashes, but this is not the point. That code it's not the point. It's not the whole thing about concurrency. So I'm not showing that, but you can check on the repository if you have any doubts about that. So, but that's it. We have a number of files, and we have phase one with each duck operating MD5 hash creation. Then we have phase two with each duck creating a pre-signed URL, and then each duck using the resources that we generated in the other tests to upload the file. So when you talk about like big O notations and we are checking about the runtime, we can see we have like a 3n algorithm, because if we have like 100 of files being uploaded, we will have 100 times each are operations, but in the end we have like just a n operation, because Big O will just not consider it all the constants. On this case, each phase it's a constant, so we have 3 phases. We will have like a big O notation of an n that will increase by the amount of files we have, and that's it. Pretty straightforward. If you want to just upload files with each phase, that's what we need. And it will be not the best thing, right? We need to each duck to wait for another duck to solve their problem so they can go through our flow. So for the next use case, we'll use promise. I don't want to explain what promises are, but you can think about like it's a asynchronous operation, and it's talking about a promise of something that we will resolve on the future or never, maybe. Okay, so we are already on our next use case about the async batches. So each duck it's still doing the same thing. So we are still using waiting for the files, and each MD5 generation right now will be a promise that we will call to resolve at once. But one thing that it's good to mention, it's we will call those promises to be resolved at the same time. That's it. Not all the promises will run at the same time, but the way we need to generate the MD5 hash, it's main thread blocking, because the library we are using right now, it's the crypto.js that does that as synchronous call. So, and I didn't want to go further with that, but it's just to have in mind that even having promises resolving are as promises, inside each promises we can have potential blocking code on our main thread, and that's a problem. So okay, we will generate all the promises we need for the M5, and then we will run that, but we are still waiting for all those promises, all those MD5 files to resolve. Then we will do the same thing for our pre-signed URLs. Then we will do the same thing for the uploads promises. So we are using batches, async batches to solve, but we are still waiting for each batch of our phases to finish so we can go to the next phase. And right now it's what we want. One thing to mention, like promise all will just wait. It's one of the promised concurrence methods we have, and it will like aggregate all the multiple promises we have to solve. But as I already mentioned, we are single threaded. So even having that running in concurrency, like we can have ducks side by side, but that's not how it works in the end, because I will explain further, because parallel execution are different from that, and we solve on another way. So that's what we have. What is the difference from concurrency and parallelism? So we have our first duck solving our MD5 hashes, our second task that is another duck creating the pre-signed URLs, and so on. For our case, we have only 3 ducks doing tasks. And actually, on the example I just showed to you, each phase it's waiting for the other phase, right? But that's not the point. So how concurrency is different from parallelism? Each duck will use the CPU to do things while it need to wait for something, you know? So each task can be split in small portions of what needs to solve, and it will processes that on the main thread as it will handle things. We don't need to think too much about that, but if we would have like web workers, and we won't talk about that today, we would have parallelism, because each duck doesn't need to share to wait the other duck to solve their problem, but here we are splitting and sharing the process of our CPUs. And here's the why we have today. You can see that you can upload files as sequential and then with batch uploads. Right now, we have like 20% faster batch asyncs than the sequential, because it will be something like that, but more like this example, because each duck will solve their problem by bit, but we have a lot of ducks running at the same time, but not sharing the same CPU time, just solving problems bit by bit, because we don't have more than one thread than main thread to work. And different from the other one, one thing that we could already be done related to the experience of the user itself would be to have like wrappers of I do the MD5 hash, then the pre-signed URLs, and then the upload, so the user can see the file upload being handled faster. But I am doing like that just to be more, to explain more about how to not do things, maybe. And you can see on the logs that the generating files are solving in different times, and it doesn't mean because of a duck started first, it will be solved first, because we are not controlling how the CPU and our queue will be handled, but it's just illustrating that a duck can start after another one and can be solved faster or not, but that's it. So different from the sequential that we have like n operations of the amount of files we were updating, the times grows like linearly with the amount of files, right? But right now we are almost doing parallel, but it's not, right? We don't have a lot of threads to work, but and why not? Why we don't have that? So browsers has like amount of connections that we can do. We have like an nginx proxy that it's handle our local stack. So we have like resource limiting by our infrastructure right now. So we have 6 to up parallel that are not parallel, but files that are being uploaded. So in the end, we don't have the time constant about our problem that's being solved with the async calls because of a lot of bottlenecks we know we have. So in the end, it will be around like 20% of improvement here. So what is like the final form of our duck today? The same duck, like I said, will solve all the problems because now each duck doesn't need to wait for the another duck to solve their problem. So each duck will generate the MD5 hashes, generate the pre-signed URLs, and perform the uploads. And that's way better because, like I said, the user will feel that the uploads are getting there. And now you can check this code that I started to write, and you can see maybe we can have some problems with that. You can see that we are sharing the result. So if I am processing multiple files as promises, as you can see, maybe when I trying to get that result, it can get in the same way of another process that it's also trying to access that memory. And that's a common problem when we have things working at the same time. We are trying to read something that maybe it's being written by another process. But just to have in mind, I am pushing a lot about this because I don't think we will have that problem with the code we have. But it's good to mention, and that's called like code racing. We have multiple processes trying to read or write and sharing resources in a way that what will happen if these happen at the same time or almost the same time, we can have problems. Because like I mentioned, we are main threaded. We can have async code working on the other threads besides the main thread. But in the end, the portion of code we are solving are not running at the same time. But maybe I will start a process, start to, I don't know, generate something while the other process are trying to read or write that resource, and we can have problems with that. So we have a topic that is called a mutex, and user usually refers to a DAX structure used to synchronize concurrent process running on different threads. So, like I said, we don't have real multi-threads running, but we have shared code, right? We can't guarantee that in some way we will have resource that is being read or write, not in the same moment, but maybe in a way that will cause us problems. So the mutex, it's like a flag that we will lock that resource, so we can be able to like stop other process to use that value while we are working with that. So this is our code. We have another use case right now, the streaming upload. We are using a library to use the mutex here because it's easier and it's just to prove a point. We have some references that we want to share between the process, and even if the UI needs to refresh for a bit, we are safe and we won't lose that state. So what we want to share? We want to share the amount of completed tasks, the amount of failed ones, and we will have like a mutex to the counter mutex that will help us to update and to read those two when it's necessary. Also, we want to, in some way, to have a file progress on each phase, because to the user it will be, I don't know, oh, okay, my file, it's almost being uploaded. So, and we want to share that with all the streaming upload as a whole, not for each process. Okay, so here it's the rest of our code. We will have like a file progress, initial progress, and just to be clear, our progress right now, it's not real, it's just fake. I will show to you in a moment. So how to use the mutex? I will create the mutex for the moment I want to set something. So for the state mutex related to the file progress, we just say, oh, I'm using the mutex right now, so run exclusive to me. If another async call or even another thread is trying to get the result from here, it will need to wait to me to consume or to update the state, and then they can take a look and do whatever they want. And for these, I will just set the file progress with the progress that I wanted. So yeah, so, and right here I can increase the amount of complete and failed from our references that we have here. And the same thing, I have the counter mutex right now inside the set result call, and here it was inside the upload file progress. So right now are just the methods that we will use on our code. It's just the interface to the each method, right? So we have the upload file progress and the set result. And when we need to update a file progress or to set a result, we are using our the mutex that we think it's the right one to do that. For the complete and failed, we are using the counter one, and to update the file progress, it will be the state one. Okay, so this is our duck solving the problems. When we call process a file, it will start to upload to generate an MD5 base hash, and you can see that we are updating the file progress with static values because I don't want it to just increase the code complexity to do this in another way. So each phase we will increase the file progress by 25, and that's it. So when I'm trying to update the file progress right here, you can see if another process try to do that, he needs to wait to me to solve that first. And then my duck will also, when we have the MD5 hash, we will update the file progress again, and then we will get assigned URL, and then we will upload the file by itself, and then we can, everything is okay. I can set the result, and if you can remember, the result, it's also using a mutex. So I'm using my results to as a completed or an error, it doesn't matter. And if another process it's also trying to set a result, it needs to wait for the another duck to do that. So that's how it's working right now. If we have like 1,000 files being selected and uploaded, all the streams will start simultaneously, but like I said, we won't have 1,000 ducks working at the same time, but I think you got the point. And we will have each duck doing all the process right now, but how it will work on the time that they need to update the counters about the results, it will be something like that. Oh, my first duck fly there first. So when he's trying to write the progress of his index, if by any coincidence another duck it's also trying to update the complete or failed count, it needs to wait for the first duck to solve that problem first. Also the same thing to upload the state, and that's it. Just to have in mind that I don't think that problem would happen with our first piece of code, but just so we can talk about mutexes and how we can have race conditions with code, and it's something good to have in mind. So if this happens at the same time that this is happening, what will be the side effects that we will have, right? And then promisal will wait for all the settled or rejected promises in the end. And that's it. And like I said in the second use case, since the beginning, we could have a duck doing all the faces, because the user would have like a better user experience. But I wanted to split each phase with a separated task so we can see if we make mistakes when sharing, splitting the code, or splitting the way we want to run the code with concurrency or whatever. If we had that duck wrapped since the beginning, yeah, each duck will need to wait for another duck to solve their problem, but the user at the same time could see the file being uploaded way faster. So in the end, having 1,000 ducks running at the same time with their lives we have like a O1 complexity. No, it's not a constant time because yeah, we have all streams working at the same time, but we don't have a core for each duck to run without any blocking time. So we don't have that. And as I mentioned it early, on this code, we have some bottlenecks related to the Nginx, related to the local stack, related to the amount of connections that our browser can do. But that's it. And this is our, this is, excuse, this is our last farm UI. You can run each type of algorithm here. And in the end, we can also take a look on each phase that is being run. So we can see we have ducks in different phases, solving different problems in different period of times. And we can see which algorithm it's faster or slower. You can see in the end, the streaming it's almost the same as the batch if you run a lot of them, because this is not a good demonstration. In the end, the both batch async and streaming will be like 20% ish faster than the sequential because of all the things I already mentioned. For a future post, maybe a future brown bag, I will talk about web workers and other ways to to have real parallelism running, because we will have more real threads and ducks running without interruption and not sharing the same CPU time. And that's it. I hope you like it. If you have any questions, just left them on the YouTube or on my repository about this specific problem. And that's it. See ya.